Thanks for the organizer to invite me to talk about Maier-Saupe field theory. To know better than me on this topic. So in this, the next 30 minutes, I will talk about first the introduction, and then we'll apply the Maier-Saupe theory for uniaxial molecules, and then for biaxial. And at the end, I will talk about Maier-Saupe in higher dimension. Okay, Maier-Saupe theory was first published in 1958 when first they published paper. It's totally written in scalar notation. So here in my representation, I will just rewrite everything in the tensorial form. Maier-Saupe theory are concerned with the polarizable molecules. So first, let's define the polarizability as a measure of how easily the positive and negative charges separate in the molecule. Is defined to be the ratio between the induced dipole moment and the external electric field. If the particle is a spherical-like, then the alpha is a scalar multiplied isotropic tensor, and the scalar will be increased with the molecular volume. But in general, the alpha is a second-rank tensor with the three principal values along three different also orthogonal directions, and the alpha, L, M, N will be functions of the length of the semi-axis of the molecules. In Maier-Saupe theory, we only consider the pair interactions between molecules, or the many-body interactions are ignored, and within the pair interactions, the London dispersion forces are taken to be the dominant one. It's also called the instantaneous dipole, induced dipole interactions. That is, basically speaking, is because of the fluctuation of the electrons will cause the instantaneous dipole in a molecule because the electron is asymmetric, distributed with respect to the nuclei. And then the second molecule will feel the dipole appeared in the first molecule, and the positive and negative charge will also separate, which result in the electrostatic attraction between two particles. If the oscillating frequency of the electrons are taken to be the same along all different directions, then the pair interaction energy between two molecules will be taken in this form. This is anisotropic interaction. This interaction not only depends on what is the intermolecule separation, and also depends on the intermolecule the vector direction r hat. And notice because you can see the two alphas will have the two orientation of the molecule embedded into these two tensors, and is proportional to 1 over r to the 6, which means if the molecules are two apart, then the interaction energy can be ignored. And then we have to write down the single molecule potential of a particular molecule due to all the other molecules in the whole system by taking the average. So this averaging process is 3 stages. So first, you have to integrate along all the intermolecule separation distance. You have to integrate over all the orientation of all the other molecules, and also the intermolecule vector direction. At the end, you have to subtract the half of the total energy of the whole system. So Peter, in his paper in 2002, discussed this issue about why you have to subtract half of the whole energy, because if you do not do that, then your final form of the free energy, you won't have the correct form. And also, so in general, when people have to carry out the single particle potential, we always assume in Maier-Saupe theory, assume the spherically symmetric distribution function, which means really the bounds for the integration limits for r hat and r are independent. So in this case, if you integrate, the integration along the r hat will be just a constant, and then if you integrate on the scalar r, then the lower limit is taken to be just a constant, which is independent independent with respect to the intermolecule vector direction. And then at the end, when you carry out this integral, it's very easy. It just equals the last line of the form. Okay, thank you. So if we, so this alpha is just really the polarizability tensor. If we take all the molecules are equivalent, then this single molecule potential is only simply taken into this form. So after we have gotten the single molecule potential, then we can go ahead, say in the thermodynamic limits, the single molecule orientational distribution function satisfy the Boltzmann distribution, and then you plug in the omega from the last page, you get this simple form. From here, if we multiply this equation both sides by alpha, and then we integrate over all the orientation, we can get this simple self-consistent equation. In many times, people also subtract the trace of the alpha to make the order parameter tensor traceless. So the self-consistent equation is generally solved numerically. So after you will get multiple solutions, so we have to determine which solution give us the preferred state. So we go ahead to have to carry out the energy is just carried out by this rho n is the number density, kT log of the single particle potential function, and is written in this form. Again, so in later slides, you will see I will subtract the trace of the alpha from this thing, and it will just result in another constant at the end that won't result in our final result. In addition, if we simply take this free energy and we are going to minimize with respect to the order parameter, will also give us back to the self-consistent equation. So that is basically the key ingredient of the Maier-Saupe theory. So now I'm going to say if we want to apply this theory to uniaxial molecules, what will happen? So the uniaxial molecules are characterized as rod-like molecules. In contrast, the biaxial molecules are characterized by this slab-shaped molecules. So for uniaxial molecules, the alphas, so instead of 3 distinct polarizability, we only have 2 distinct ones. So alpha m equals alpha n, then we rewrite this alpha in terms of using this interesting form. So this is really the anisotropic part of the polarizability and plus the isotropic part. So at the end, the isotropic part do not really contribute to the free energy in this simple case. So we plug in this into the single molecule potential. At the end, we have this form. And from here, we can identify our order parameter tensor and the single molecule orientation descriptor. Q is defined to be this 1/2 3 LL minus I. It's a little bit different from Dr. Verga's definition just because of the renormalization. Okay, so this constant is due to this isotropic part of the polarizability. And then we just follow the procedure, write on single molecule orientation PDF, multiply both sides by Q and integrate. We got this self-consistent equation. We can solve that numerically. This is a five equations, but more simply, we can say, okay, the Q traceless symmetric in its eigenframe, it can be characterized in this form. So we say, okay, if Z, okay, so it has been proved by 3 groups in 2005 that P is always equal 0, so which means finally, actually, your Q is always uniaxial if Z axis is taken to be the eigenvector associating with the distinct eigenvalue here. So at the end, we only need to care about what is the value of S. So we can simplify our self-consistent equation, only write down the self-consistent equation for the order parameter S. So this is really, this is equivalent to S is average of P2. So here is the solution of the self-consistent equation, very famous. So the horizontal axis is the reduced temperature. When temperature is very low, its nematic phase is stable. High temperature isotropic. We have multiple solutions. We have basically 3 solutions at low temperature for each at low temperature. In order to determine which one is stable, we have to calculate free energy for each solution, and you can see that the lowest energy is colored by the black, and you can see at the transition temperature, the lowest free energy is changing continuous, but the first order derivative is discontinuous. So that is a characterization of the first order transition. So here are the comments of the Maier-Saupe theory is the first successful molecular theory predicting the nematic phase qualitatively. Is totally analogous to the Weiss theory of ferromagnetism. Dispersive attractive force dominates, which favor parallel alignment of molecules, which is the key to the nematic phases. It predicts the first order isotropic nematic transition is basically because of Q and negative Q correspond to a different physical configurations. And also the order parameter S tends to unity as T approaches to 0. In this theory, it has simplified assumption is assumed a spherically symmetric distribution, which just means the molecular shape is not really considered and the short range repulsion is ignored, even for the molecules which are spherical-like, and if they have anisotropic polarizability, they can still form the nematic phase. So I say the molecular shape, if you really want to take into the molecular shape into consideration, you can see from this picture, this is only 2D ellipses. This just tells us the intermolecule separation R will really depend on the intermolecule vector direction. So it could be varied by a factor of the aspect ratio in different directions. But work has been done to include the steric interaction into Maier-Saupe theory. So Gilbert in 1977, they include this generalized van der Waals interaction into account. And Peter and Bergersen in 1987 also have done some work by considering the single particle potential by taking into account the steric interaction, which is a linear relation with Q squared, and he predict with the higher transition temperature and the lower order parameter S. And also, relative recent work by Sonnet and Verga also has done some work, and I think Sonnet will talk about this tonight. A more general pair interaction, including the quadrupole interaction, which is the P4 term, has been considered to improve the quantitative prediction in 1972 by Hemsbier. Connection, there's relation between Landau, Dijon, and the Maier-Saupe if we do power series expansion with Maier-Saupe potential with respect to Q near the transition near to Q equals 0, you can recover the Landau Dijon form of bulk free energy. But in Landau Dijon's energy, I just want to remark that the Q there is not really related to any physical parameters. And also have a relation between the Maier-Saupe and the Onsager theory for hot rod. So in Onsager theory, there's no energy, only the entropy term. However, after we carry out all these complete calculation, you got the excluded volume, which is really the sign between these two two major axes. If you do the multiple expansion of the excluded volume potential, you can, to the very first term, you recover this Maier-Saupe potential. And this is when people doing the liquid crystal polymer simulation, they always replace the Untitled potential with the Maier-Saupe potential. Even they have taken the same form, but they just have a different physical meaning, because Maier-Saupe has a temperature dependent, but Untitled doesn't. Okay, so that is the uniaxial. If we apply the standard theory to biaxial molecules, which are taken, all the polarizabilities are taken to be different, then you, if you carry out single molecule potential, here we can redefine this whole quantity, which is really the polarizability subtract the trace and renormalize a little bit. We identify this, which also normalized by the sum of the alphas to be our order parameter. This is the average of that is order parameter. And this work for the biaxial molecules, the original work has been done by Fraser in 70, but his work is using the spectral tensors. So we reread his theory into the tensorial form in last year. So the rest is followed the general procedure very easily. So we first write on the single molecule potential from here, Boltzmann distribution, and then we get a self-consistent equation. So now, again, in order to solve the self-consistent equation, here we cannot assume p equals 0 anymore. But however, so here, if both s and p equals 0 is corresponding to isotropic phase, if p equals 0 is uniaxial, and if both are not 0 is the biaxial phase. We solve that by using this is the representation of the three orthonormal axes. After that, we only get instead of the 5 equations, we only need to solve this 2 equations for these 2 order parameters, s and p. Again, we call s is the uniaxial parameter and the p is a biaxial order parameter. A feature I have to say here is here, both s and p will not only depend on temperature, but also depends on these molecular parameters alphas. We have 3 alphas here. So in order to present our final phase diagram, we are going to use this idea of a ternary diagram. We normalize our polarizability. So the ternary diagram, the idea is really for any points inside this equilateral triangle with a side 1, if we project these points along each side, to each side along the direction of the sides, we get the line segment with sum over to 1. So each point inside this equilateral triangle will corresponding to a set of the molecular parameters. Due to the threefold symmetry and the mirror symmetry, we only need to consider this area, which have the alpha L is bigger than alpha M, bigger than alpha N. All these other areas are just permutations of these alphas. In this little red triangle, the short side is corresponding to a disk-like particle, and the hypotenuse is corresponding to the rod-like particle. Along this bisector of this angle is corresponding to this very special shape, which is the difference between the largest and the second polarizability is equal to the difference between the second and the smallest polarizability. We add to the triangle to a vertical axis, which is a reduced temperature, and the plane, the triangle in the plane is corresponding to the material property. So here, the red surface is corresponding to the isotropic nematic phase, first order phase transition, isotropic uniaxial nematic phase transition, and these two blue surfaces are representing the second order uniaxial biaxial phase transition. And these three surfaces are intersecting along one line. This is really the bisector of the angle, with corresponding to the second order phase transition directly from isotropic to biaxial phases. So that is the main result. But we want to, if we do a reparametrization using r and theta to represent these alphas, we find out, so r is kind of the measure of how far of our particle is deviated from the spherical shape, and theta is a measure of how shape anisotropy of the particles. So along each arc here is corresponding to the same r. Along each ray emanating from the upper vertex is really the same theta. After the calculation, we noticed that our final result, the phase diagram will only depend on theta, and r just simply rescale the temperature. So if you look at this this graph, this is for a fixed r. So this is kind of a symmetric phase diagram. So this is corresponding to theta equals 0, which is really the measured from the hypotenuse, is corresponding to rho, and rotate clockwisely to the short axis, which corresponding to theta equals 3 over pi is the plate-like particles. And in the middle of this horizontal axis is corresponding to the spatial shape of the particles, which is optimal configuration for the biaxial phases, because you got the direct second order phase transition from isotropic to biaxial phases. That is really the simple application of the Maier-Saupe to biaxial phases. For these other biaxial mean field models, for example, this Luckhurst et al. Proposed a general power interaction, including all different interactions, not only the pairs. And Straley in 1974 is a general power interaction via spherical tensors. He got 4 scalar order parameters. And Sonnenberg and Durand use a tensorial notation to rewrite its potential. And in addition, they found a critical point on the phase diagram where the second order transition from uniaxial to biaxial phase become first order. Okay, so that is the for biaxial molecules. So finally, I'm just talking about just for fun how the Maier-Saupe behave in higher dimensional space. The motivation is from here. So if we consider a one-dimensional model, which means you have rod-like molecules, they are all oriented in the one-dimensional lattice, one-dimensional space, then there's no degree of freedom of the orientation at all. So all the molecules are always in nematic phase, so no transition. In 2 dimension, people predict second order transition. In 3-dimensional is first order transition. So we are asking the question, how does the behavior depend on dimensionality? So we consider axisymmetric particles in 4 dimensions, which means one axis is different from all the other axes. For pair interactions, we just only need to modify it slightly. So here alpha is a 4x4 tensor. We have to modify that R to the 6 dependent to R to 8. However, this doesn't really change too much. The single molecule potential is written again in this very similar form. The only difference is the Q is normalized a little bit differently. Self-consistent equation is still taking the same form. So we solve it. So here, Q is a 4 by 4. We want to parameterize our eigenvalues and using this 3 order parameters. So in addition to S and P, we add another V here. So we are going to solve it. We have single unit vector in 4 dimensions. So here we characterize this this unit vector in 4 dimensions using this simple generalized spherical coordinates. Subconsistent equation for this Vs and P is simply in this form. Not important. However, the final solution, we got 3 different solutions for for the low temperature. So we have isotropic phase for higher temperature. So all these VSP are equal to 0. We got also uniaxial solutions. That is this the purple color, the solution. V is non-zero, but both S and P are equal to 0. This corresponding to the uniaxial phases. So we say, okay, V is our uniaxial order parameter, and both S and P are biaxial order parameter. And then we get a third solution, which is the brown color. The third solution is symmetric with respect to the y-axis. We get V is not equal to 0, but P equals 0, and we have the relation between S and V. This is really corresponding to this kind of Q, which as each of the 2 eigenvalues will be the same. Okay, and this is the bifurcation. We again have to calculate the free energy corresponding to each solution. Again, is a first order transition because of discontinuous on the first order derivative of the free energy, first order. So there's no big surprise here. Now we're going to put all these dimensional results together. Because of the increasing of the dimensionality, there's more degrees of orientational freedom. That will cause the increase of the entropy. Because of the increasing of the entropy, the nematic phase will harder and harder to form. This will result in the reduced transition temperature decreases with dimensionality. So it's hard to see from picture, but really this is for 2D, the reduced transition temperature, 2.22 here, 0.22 here is the 3D temperature transition, and the 4D transition is slightly lower than 0.2. Okay, also due to the increase of entropy at a given reduced temperature, the order parameter decreases with the dimensionality. Okay, the last thing I have to say is the interesting observation between these different order parameter in different dimensions is, you can see here is our S in the definition of S in 4D. You can see the relation between this 4D and the 3D biaxial order parameter, and also the other biaxial order parameter is related by really the 3D order parameter multiply the same factor. So I want to ask whether this is always true. So we also want to look into what happened in 3D and 2D. So this is the definition of the P in 2D, and we can see the similar relation. So there's just an interesting observation between the scalar order parameters between different dimensions. Okay, I think that is the end of my talk with the summary here. It's a Maier-Saupe theory, is a mean field theory, only consider the pair interactions, and also I forgot to mention that we only consider the single molecule orientational distribution. Nonpolar molecules interact via random dispersive forces and can describe both biaxial and uniaxial particles, and the behavior depends on dimensionality. People can also make effort to extend this Maier-Saupe to spatially inhomogeneous systems. Okay, so that is the end of my talk. Thank you for your attention.
Okay, thank you for your talk, and in particular for being concise. Because indeed we have been running 10 minutes late when you started, and now we are on time. So I think we can afford a couple of questions.
Xiaoyu, at the end of your section about the uniaxial molecules, you made a remark about the relation between Maier-Saupe theory and Landau-de Gennes theory, right? And you said something about how the order tensor in Landau-de Gennes theory does not have a physical meaning. I may be misquoting you, but can you clarify what you were saying in that remark?
What I meant is the Q in Landau-de Gennes theory do not have a clearly definition. It only requires symmetric and traceless. It can be any symmetric traceless Q. It can be defined as the Q in my case. It also depends. It can define to the the average of the major axis minus the sum minor the minor axis. So in my case, it's defined by the average diet of LL, but in other paper in the literature, they can also define it to be the LL minus MM, the average of that.
Okay. I mean, it sounds like you're being a little bit hard on the Gennes there. But,
in the original de Gennes paper, they defined it to be the dielectric tensor, right?
Right.
So just all different kind of definitions of the Q.
Okay.
That is what I meant.
Okay, please.
What's the physical meaning of four-dimensional Maier-Saupe theory? Actually, most cases you can think of the four-dimensional is like the coordinate, three the odd angle. At that time, the three odd angle is not exactly of the four-dimensional. So what is exactly of the physical meaning of four-dimensional here?
There's no physical meaning. I cannot really say explicitly what is a four-dimensional rod looks like, but it's not Euler angles. Euler angles are corresponding to biaxial particles. It's different.
Okay, any other questions? Maybe in this case I can make a short comment, and that it's perhaps important to mention that Maier-Saupe theory is a particular case of the so-called molecular field theory, which is used in many other areas. And there are general ways how this theory is derived from more general statistical mechanical expressions. And that's first thing. And then second thing is that you mentioned the relationship with theories where steric interaction is taken into account. In fact, I mean, because Maier-Saupe theory is for fluids, steric interaction is inevitably taken into account there. Otherwise, the average intermolecular potential just diverges. And so in this way, I mean, there is an even much stronger relationship with more general approaches. So I hope that during the course of this program, we will go deeper in all these problems, and we will discuss them later also in our second workshop. So thank you very much again.